In this video, we're going to go ahead and calculate the line integral for the vector field that's bounded by this particular curve, which is represented by the circle here with radius 3. In order to solve this, we're going to use what I think is one of the most powerful tools in multivariable calculus, and that's Green's theorem. So what exactly does Green's theorem tell you? Let's just say, for example, that we're trying to take the line integral of this vector field. And what that is you have all these little vectors here, and we're trying to find the line integral about this curve C. Now, what exactly is the line integral for a vector field? It's really telling you how much the vector field or how much flow of this vector field goes around this curve. So in order to solve for that, sometimes this could become a little tedious. Green's theorem tells us that we can actually take the double integral of this particular region. That's the region D, that's where it's bounded by. And you're gonna take the double integral of this expression here. Now, I guarantee that there's plenty of people that know how to explain Green's theorem much better than I did, so please feel free to let me know in the comments how you would explain it to students. So if we're gonna find the line integral for the vector field, we're gonna identify this as P, and that is gonna be Q. So in order to solve the double integral, we're first gonna go ahead and find the partial derivative of Q with respect to X, and that's gonna be the partial derivative of this function right here. So the partial derivative of Q with respect to X is going to be the partial derivative of this function here, 7x plus root y fourth plus 1. And now, if you remember, or if you don't know much about partial derivatives, the idea is to treat every other variable but the x as a constant. So in this case, y to the power of 4 plus 1 is just simply a constant. So you're just taking the derivative of this value here. So we just have 7. And now we're going to do the same thing. We're going to go ahead and evaluate the partial derivative of p with respect to y, and that's going to be the partial derivative of this function right here. And that's 3y minus e to the sine x. Ooh, this one's going to be interesting. Once again, if we're taking the partial derivative with respect to y, I was thinking for whatever reason it was going to be x, so I was getting excited to take the derivative of that. But anyway, you're going to treat the x as a constant in this case, and that's this. The x just doesn't matter. It's a constant. When you take the derivative, that's going to become 0, so we're just really taking the partial derivative of this with respect to y, and that's just going to be 3. Ooh, so far so good. So now we're going to go ahead and start applying Green's theorem. So again, if I want to take the line integral of this vector field, then all I really have to do is take the double integral bounded by the region D. And in that case, it's going to be this region, which is bounded by the circle with radius 3. And now we have partial derivative of Q with respect to X, and that's going to be the 7. Minus the partial derivative of p with respect to y, and that was 3. And now we're taking the double integral of this. This is just going to become 4. We'll take care of that in a second. But let's go ahead and find some parameters. Now, I don't know if I want to do this in terms of x and y. I'm going to change this in polar form. And it's going to be much easier. If we're going to use polar form, then we're going to have x is equal to r cosine theta. We have our y is going to equal to r sine theta, and now our parameters are going to change. R is going to go from 0 to 3, and our theta is going to go from 0 to 2 pi. So we have new parameters, 0 to 2 pi, and then we have parameters 0 to 3 of 4, and then now we can't just use dr d theta because we have to take the Jacobian of this. Now the Jacobian helps us find the new differential based on the parameters that we're using. And in this case, it's just going to be r. That's something that I can talk about later on, but this is exactly what we're going to integrate. So now in order to integrate this double integral, we're going to go ahead and integrate this one step at a time. So we have this first integral here with respect to r. So we have the integral from 0 to 2 pi. The integral of 4r is just 2r squared, so we have 2r squared from 0 to 3 with respect to theta. And now we just implement the first fundamental theorem of calculus. Plugging in the value of 3 gives me 3 squared, 9 times 2, that's going to be 18, minus when you plug in 0, that just goes away. So we really just have the integral from 0 to 2 pi of 18 d theta. And now we just go ahead and integrate this. Very simple. We have 18 theta from 0 to 2 pi. Plug in 2 pi, we get 36 pi minus when you plug in 0, that's just going to be 0. And this right here is the vector or the line integral for the vector field for this function right here. And we solved it using Green's theorem. And I think that's pretty nice. And that's going to do it for today's video. I'm going to try posting more frequently. So if you have any ideas of what I should post about, let me know in the comments. In the meantime, feel free to subscribe, follow me on Instagram, and of course, if TikTok is still around, please follow me on there. I'll see you on the next one.